Some initial definitions are important. Barrier is an individual landform. Barrier system is a multiple interrelated barriers within the context of an overall coastal setting. Barriers are elongated, narrow landforms composed of sand and other loose sediments transported by waves, tides, currents, and winds. The term barrier identifies the structure as one that protects other features such as lagoons and salt marshes from direct wave attack of the open ocean. Look at this example here in Brazil. Most barriers are oriented parallel to the general shoreline trend, with their crests above high tide level, distinguishing them from bars. Barriers are potentially mobile and usually separate marine or lacustrine open water bodies from marshes, lagoons, and estuaries that may be connected to sea or lake by tidal inlets. In this image, we can see a tidal inlet that connect inland waters to the ocean, and the tidal inlet is protected by coastal structures. Barrier systems are a series of barriers and their associated environments along a coastal compartment defined on the basis of a common setting or sediment source. They may contain a series of similar barriers, but commonly include a range of barrier types. In the satellite image, also here from Brazil, we can see a barrier system composed by a long beach ridge plain and by some lagoons and a narrow barrier that separates the lagoons from the ocean. Barrier systems are also a composite of various small-scale coastal environments, including beaches, coastal dunes, salt marshes, and tidal flats, mangrove shorelines, tidal inlets and tidal deltas, and the shore face. Look at this model, and then look at this example. Barrier systems fringe about 15% of the world's seas and oceans, and they are equally common along lake shores. They occur on all continents except Antarctica and at all latitudes. Their distribution is very uneven, however. This uneven distribution is a function of a tectonic setting. About three-quarters of barrier coastline occupies low-relief coastal plains on trailing edge continental margins, including marginal seas, mostly under microtidal regime, such as in the east coast of South and North America east coast of Australia, southern Africa, and western Europe. Take a closer look on the map. Barriers can be classified by their plant form and then by several parameters. For example, attachment versus detachment, tide versus wave dominance, island length versus inlet width, open water versus fat limited exposure, drift versus wash alignment, single versus multiple barriers. And so there is significant variability in barrier shape. About the classification of barriers regarding their detachment or attachment to the mainland, there are the no free end barriers that can be illustrated by tombolos, bay-mouth barriers, mid-bay barriers, and others. There are the on-free end barriers, and maybe the spits are the most common barriers in the world. They can be underclassified as constrained bay-mouth spit, continuation spit, flying spit, among others. There is also one free end barrier like the cuspate foreland, and then are the two free end barriers like barrier islands. Let's see a little more about those types of barriers. No free end barriers are barriers built from one shore to the other across bays and estuaries. Natural tombolos are barriers that link islands to each other or to the mainland coast. Baymouth and mid-bay barriers or bayhead barriers form in response to littoral sediment transport at the entrance to a bay or along the sides within a bay. And as I said, there is tombolos, baymouth barriers, and mid-bay barriers that we can illustrate. Tombolo may be a common coastal landform in the world. Tombolos attach an island, usually or glacial or volcanic origin, to the mainland by spit growth. The island serves to anchor the barrier. Baymouth barriers are also common, mostly in microtidal areas where the low tidal range inhibits inlets except when breaching occurs during a major storm. With the restriction of salt water input, freshwater or brackish marshes will develop. Barriers are sometimes artificially opened to improve clam production by maintaining salinity levels. Bayhead barriers are found in the upper reaches of a bay and form where the outer coastal cliffs are resistant to erosion. While some sandy sediments may be supplied from the cliff erosion, much of the material necessary to form the barrier feature is derived from other sources, like the intercontinental shelf. Now let's see some of one-free end barriers. They include a wide range of spit forms where there is a pronounced littoral drift from one direction, and cuspate forelands that form where there is a convergence or littoral drift from both directions. Spits are much more numerous than cuspate forelands and worldwide may be the more significant than barrier islands. Like I said, spits are formed as alongshore currents move abundant sand and gravel from eroding cliffs into open water. Spits elongate in the general direction of littoral drift and therefore represent the net movement of sand along the coast. There are many kinds of spits. Here are some examples: a simple spit, a double spit, a recurved spit, and complex spits. Cuspate foreland forms where there is a convergence of littoral drifts from both directions. They require that littoral drifts from both directions be of the same order or magnitude, otherwise a spit would form. Now talking about two free end barriers, there is the barrier islands that occur on gently sloping coastal plains and tend to form chains of islands. By strict definition, they should have two free ends, but some barriers in a chain may eventually be attached to the mainland, and it's probably best to consider the whole chain as a barrier island. Barrier islands exhibit a wide range in size and overall shape. This diversity stems from large variations in sand supply, tidal range, and wave energy. In this image, we can see four types of barrier island. The first one, mesotidal regressive barrier island. Like the name said, it occurs on mesotidal regime and it was formed by regressive sea level conditions. The second one is the microtidal regressive barrier, formed during regressive sea level conditions also, but in a microtidal regime. The third one is the mesotidal transgressive barrier island. And the next one is the microtidal transgressive barrier island. Those are formed in transgressive sea level conditions, maybe by processes of overwash. If we just look at their differences, we can see clearly that there's a difference in width. Regressive barriers are thicker than transgressive barriers. Barrier classification can be also a function of wave and tide dominance. Mixed energy barriers are commonly short, separated by prominent tidal inlets. The stronger the tide dominance, the shorter and more stunted the barriers. Wave-dominated barriers are commonly narrow and long with few small inlets. And so, considering tidal range and mean wave heights, barriers can be very different and usually not difficult to distinguish them. As long as the tide dominates, the barriers are more stunted and shorter, and as long as wave dominates, longer and narrower are the barriers. Let's see some examples. Barrier classification should also consider their internal structure and temporal development. Beach ridge plains are formed with regressive sea level conditions and consist of sandy or gravelly wave-formed ridges that may contain abundant shells and shell fragments. Fordham ridge plains consist of series of ridges formed by wind deposition and stabilized by vegetation, and the Chenier plains consists of sandy and shelly ridges overlying muddy deposits. In the image, we can illustrate the three of them, and the most important structure is that time-dependent parallel deposition of those ridges. And about these time-dependent parallel depositions, we have these three models. The A is retrogradational, B vertically accreting, and C progradational. Their differences depend on sediment viability and on recent sea level fluctuations. Many barrier system sequences contain both transgressive and regressive elements, reflecting temporally changing and spatially varying ratios between changing of the accommodation space, sea level oscillations, and sediment supply. In retrogradational systems, barriers migrate landward over back barrier deposits. They evolve during transgressive sea level conditions and may be also known as transgressive barriers. So please don't forget that retrogradational systems occurs during sea level rising conditions and forms transgressive barriers. Rising sea levels lead to landward migration of the beach and dune system and reworking of the inner shore face. The barrier overrides marsh and lagoon sediments, which are later eroded as they become exposed at a seaward side. If sea level rises too quickly or there is insufficient sediment in the system, then the barrier may be drowned by leaving portions of the barrier and lagoon sediments stranded on the continental shelf. Please take a closer look at some shapes of transgressive barriers around the world. The second one are vertically accreting barriers. In these systems, barriers migrate very little, showing planform stability during thousands of years regardless of sea level variability. And so in these systems, the only movement is vertical movement of aggradation. progradational systems, barriers migrate seaward, capping thick accumulations of shore-face sediments. They evolve during descending sea level and are also known as regressive barriers. Beach and dune sands build out across upper and lower shore-face sediments, and back barrier marsh and washer fan sediments overlie lagoon sediments, but development of new far dunes ridges reduces the possibility of new overwash occurrence. And like the first one, please don't forget that progradational systems occur during the drop of the sea level and forms regressive barriers. Let's exemplify with some images. This is a schematic profile of Holocene regressive barrier at Paranaguá, South Brazil. In this model, the number 2 in a lighter shade of gray is the Holocenic regressive barrier that evolved over the accommodation space of the number 1 in a darker shade of gray, that is the Pleistocene substrate. Those numbers in the image indicate the history of deposition from 4.2 thousand years ago, and then 4.1, 3.9, 2.8 thousand years ago until nowadays, where is represented the MSL or mean sea level position. The next image shows how this looks like in nature. And here we have some few examples of regressive barriers and their appearance along the world. Like we saw at the beginning of this class, the barrier system have many components. Here are some of them. Firstly, the mainland, including bays and estuaries extending some distance inland. Then, a lagoon, a bay, or extensive marsh that separate the barrier from the mainland. The subaerial barrier, including beach, dune, and back barrier deposits. And then there is also subaqueous platform of sediments, the shore face extending offshore from the exposed beach, and inlets and associated tidal deltas. Barriers are very dynamic systems. Overwash is one proof of this. Overwash may occur on mainland dunes when the foredune is breached and sediment is carried into the landward swale. Overwash is typically characteristic of transgressive barriers because they are relatively narrow and the volume of sand in dunes is more limited than in stable, vertically accreting barriers. The effectiveness of the overwash depends on some factors controlling them, as the intensity and duration of storms, wave heights, tide range, fortune characteristics, and etc. The resulting sedimentary deposit of the sediment transported by overwash is termed a washover fan or washover terrace, depending on the lateral extent. In the left image, there's a flowchart that compiles factors around the overwash process. The overwash process depends on storm characteristics regarding its intensity and its track. Depends on the storm surge characteristics like elevation, duration, wave height. Also depends on coastal morphology, mainly its orientation relative to storms, bathymetry, beach width, and overall volume of sands. Depend also on tides and their range, and on foredune characteristic, as a foredune can be a coastal protection structure or not. The overwash process leads to beach erosion and dune scarping, and the result registered in the landscape are the washover deposits that you can see on the right image. Simply, the washover deposit can be a fan type or terrace type. Another dynamic feature of barriers are the tidal inlets. Tidal inlets are openings that separate barrier islands, portions of a barrier spit, bay mouth or bay head barrier, or lie between one end of a barrier and the mainland. They provide the connection between the sea and the lagoon, bay, or estuary, landward of the barrier, and allow the exchange of water between these two water bodies. The exchange of water is driven primarily by the rise and fall of the tides. Where there is substantial freshwater inputs to the lagoon, the volume of the ebb flow may be enhanced over the flood. On some microtidal coasts, where barriers close off a river mouth, inlets may only open seasonally when flooding from rivers or lagoons are huge. Some inlets may be artificially opened, and some others remain open with coastal structures. Inlet morphology reflects the interaction between flows through the inlet entrance, sand transport by wave, and the evolution of the two ends of the barriers on either side of the entrance. Sand is deposited at either end of the inlet entrance because of the increasing channel cross-section, decreased flow speed, and on the ocean side, the interaction of the ebb flow with waves. This results in two large depositional sand bodies, an ebb tidal delta on the seaward and on flood tidal delta on the landward side of the inlet. Along the coast, longshore currents move sediments alongshore in volumes that would fill inlets in absence of tidal currents. Sediment carried into the inlet throat is constantly swept away by tidal currents. Sediment moved landward by flood currents is deposited in a sandbar inside the inlet called a flood tidal delta. The sand transported seaward by the ebb currents form a seaward lobe called the Ebb Tidal Delta. Please take an attentive look at this image. There are in the outside dominant waves. There are some features like recurved speed and a barrier island. In the middle, there is the inlet and the inlet's throat. Inside the inlet, as the left on the image, it forms the flood tidal delta. Outside the inlet, it forms the ebb tidal delta. And there are some other features represented in this image, like the swash bar, the marginal flood channel, and the sand waves, etc. This is a flood tidal delta example, and in this model there are some features specifically for the flood tidal delta. There is the flood ramp, the flood channel, the ebb shield, the ebb speed, and the spillover lobe. All of these features we are going to talk more specifically later on in this discipline. In this photograph, there is an example of a massive ebb tidal delta, and in the smaller picture, we have the Ebb Tidal Delta and their main specific features like external terminal lobe, the swash bars, the marginal fluid channel, the main ebb channel in the center of the image, the channel margin linear bar, and other examples we will study further on this discipline. And for today, see you soon, take care and be safe.